Okay, so let's go back to here. So we have 3 qubit, right? Q2, Q1, and Q0. And now our goal is to understand how to measure it. So how many classical qubit do we have in this circuit? Classical qubit. 4. Yeah. Or you can say you cannot because it's too small. It's 4 qubit, right? 4 classical bit. Why is 4? Because it says so, because I did so, not because of any physics law, right? I just decided to have 4 classical qubit over there, okay? Now, so at A, what are the possible value? I mean, now remember, everything initialized to 0, including the qubit and also the classical qubit at the beginning of all our quantum algorithm. So now at A, what's the value of the 4 register, classical register? So you should understand there are 4 bits, 0, 1, 2, 3, right? So that's why I put it here 0, 1, 2, 3. At A, what are the value? I just told you it initialized to 0, so they must be 0, 0, 0, 0, right? Make sense? Then I apply a NOT gate to Q2. What will be the value in the classical qubit? Try to imagine you are the quantum computer plus the classical qubit, and someone applied the NOT gate to Q2. What will be the value in the classical qubit? Nothing happened. Exactly. I just apply a quantum gate to Q2. So if I try to read out, it will still be 0, 0, 0, 0, right? Then I say I want to do a measurement. This time the measurement is at qubit 2, and I assign it to register 2. Okay, again it counts from 0, 1, 2, 3, right? Assign it to 2. So what will be the value now? Because I read qubit 2, what is the value of qubit 2 now? Q2. It was 0. After the NOT gate, it becomes what? 1, right? So when I read it is 1. Then it is going to store 1 in 2. That's why I have 0, 1, 0, 0. Make sense? Okay.
But your B is 0, 0, 0, 0, right? But you're saying
B means at this stage, what is the value of C4? Yes, 0, 0, 0, 0, 0, 0.
Before the measurement.
Yeah, before the measurement. Yeah, it's the 9, exactly. Now, then I do one more measurement at qubit 2. But this time I store into register 3, right? Or, yeah, classical bit 3. And at D, what is the value of the classical qubit? What did I just do? I store 1 to 3, right? So I get 1, 1, 0, 0. Is this clear? Make sense? And then I have another measurement, but this time I measure Q0 and I store it to register 3. What will happen? Q0 will give me what when I do the measurement? 0 or 1? 0, because everything starts from 0. I didn't apply any gate, right? So 3 will become 0 again. And now I try to plot it at E, right? This is the plotting at E. Means I try to plot the value of the classical register. I get 0, 1, 0, 0. Make sense? Is this clear? Any questions? If no question, let's take a look at another circuit. Now, this circuit is like this. We will have still, let me call it A at this 9, B, C, D, E, and then F, right? So let's look at this one. Firstly, again, we have how many classical qubit? 4, right? 4 classical qubit. And I still call it the third one, second, first, and 0th. Okay, at A, what do we have? How about let's just go through the class. You want to try? At A, what do we have? 0 everywhere because we just initialize it. Thank you. We want to try B. So after, right before B, we apply a NOT gate to 2, right? And what happened at B? What's the classical register? Still all 0. Why? We didn't do measurement. We didn't touch the classical qubit. Okay? Now, how about at C? We done a measurement at Q2 and store it in the second register. What is that? I mean, give me everything. 1, 0, 0. But I will have 4 classical qubit. Can you give me all 4? 0, 1, 0, 0. Very good, right? Everyone can follow? It's the same as last time, right? Now then we have a new symbol which is very useful here. It means control knot. But this control knot is a little bit complicated. It means that if C4 equals to 4, that is what it means. If the classical register equals to 4, and what is 4 in binary? 0, 1, 0, 0. Okay? So here, what you mean, this is not really control knot. I confuse you. It's classical, right? Just a if-else condition. The computer will say, look at the classical measurement. If it is equal to 4, apply a NOT gate to qubit 1. If it is not equal to 4, don't do anything. That is the meaning, right? So now, at C, so I jump a little bit. We have not finished D yet. I'm sorry. So I jump a little bit, right? C is 0, 1, 0. What is D? Can someone tell me? What is D? D, before D, we did a measurement on qubit 0 and put into 3, right? What is that? Okay. 0, 1, 0, 0. Because Q0 is 0, and I put in the third qubit, right? Now, how about at E? E says that not at E, right? Right before E, it says that if this equal to 4, which means if this equal to 0, 1, 0, 0, apply a NOT gate to it. So what is the value at E? Zero, 1, 0, 0. Why? Thank you. Yeah. At E, yes, we applied the NOT gate to Q1, but we have not done any measurement, right? So this is still 0, 1, 0, 0. Okay? But at F, we have done a measurement at Q1 and applied to 1, right? So what would that be? Anyone? Zero, 1, 1, 0. Because the value of Q1 is now 1 because we applied the NOT gate. So when we measure it becomes 1, we put into register 1, so it becomes 0, 1, 1, 0. As a result, at the end, we see 0, 1, 1, 0 in this simulation. Is that okay? I'm going very slow, but it's good to go through this. This circuit is the same as the top one, except that I changed the condition to equals to 3. What does it mean? Anyone can explain to me? condition on C4 value equals to? The classical register equal to what? 3? No. Yeah. Equal to 0, 0, 1, 1. Right? That is 3. If it is equal to 0, 0, 1, 1, then we will apply the NOT gate. Will it apply the NOT gate based on what we say? Because this is basically D, right? It won't. So in this circuit, it's not going to apply the NOT gate. So eventually, you will just get 0, 1, 0, 0. Okay? So go back to check yourself. Right? The very reason is just that this one is not going to get applied. So here you will have 0, 0, 1. Right? And these are all the measurements in the right order. 2 to 2. Not really. 0 to 3. 0 to 1. Right? So that's why you get 3, you have 0. 2, you have 1. 1, you have 0. And then the 0th qubit is 0. So try it. Try it yourself. I'm not going to talk about, okay? But here I introduce you the conditional operation in Qiskit. Okay. Then why I want to do that? Because I want to discuss how to implement quantum teleportation in Qiskit. Right? So if you remember, you probably don't. In quantum teleportation, what we do is that we have 3 qubits. First, the first Bob is going to do an entanglement between his qubit and an ancillary qubit, BB, to form this entanglement. Right? It's halves 1 over square root 0, 0 plus 1, 1. Then he will send this qubit physically to Alex. This qubit sent to Alex. So this is in Alex's lab. Alex has a qubit which is alpha 0 plus beta 1, right? And then she will do an entanglement. You just take it for granted if you forgot. But the most important thing is what? Alex will try to measure the middle qubit, BB. If she got 0, he will just give a classical call, right? Give a call to Bob and say, I got 0, so you don't need to do anything because now our qubit got entangled successfully. If she got 1, she will call Bob to apply a NOT gate to his qubit so that 010 become 011 becomes 010, 110 become 111 because Bob's qubit is at the end. Okay, I'm not going to go over this teleportation again. You can study from last lecture, but the main point is to remind you that Bob will apply identity gate or NOT gate based on Alex's measurement. Is that okay? We still have one more step to finish the teleportation. This step is only to form entanglement. Here, Alex will measure in the plus minus basis. And then if she got plus, she will call Bob, and Bob say, okay, just don't do anything. I already got your qubit. It's quantum teleported to me already. If she got minus, she will call Bob, and then Bob will apply a phase shift gate, the Z gate, so that he will get the qubit state of Alex in his qubit. So again, 2 measurements, but this measurement is the plus minus basis. Okay? Now then we can look at a Qiskit implementation of this teleportation. This is just good for instructional purpose. Let's first, this is step A and B. Again, we have 0, 1, 2. The top one, I call it Bob. Middle is BB. The bottom one is A. And how many classical qubits do we have? 3. And why?
You gave it 3.
Just I put it 3, right? If I put it 2, might not be meaningful because we cannot, maybe it's okay, but I need some special treatment, right? Putting 4 is too many. I just put it 3 because I want to have one classical qubit correspond to every to one quantum qubit. Just I want to have a one-to-one correspondence. Now, the first thing you see that Alex, actually I kind of swapped this one. No, sorry. Bob is going to do an entanglement for his qubit, Hadamard gate and control NOT gate. Right, take a look here. Hadamard gate, control NOT gate. So this is okay, right? When you see identity gates are just to fill up the space so that we can have the right indentation. And after this, Alex is going to apply a control NOT gate. After this, apply control NOT gate. And of course, in Qiskit, I don't need to really physical send a qubit, right? Because this is just on a chip. We're just doing emulation. So this completes step 1.1. So what do we need to do now? We need to do measurement and then decide if Bob need to apply a identity gate or X gate. So here, Alex did a measurement. Do you see that? And she will assign this to classical qubit 1. Okay? Classical bit 1, the middle one. And then here we say, if the register, again, it starts from 0, 0, 0, right? Because I should not use bracket. This one starts from 0, 0, 0, right? C3? Correct? But at this stage, it is equals to C3 equals to 0, 1, 0 if BB collapse to 1, which is here. If Alex measured BB, she got 1, then it collapsed to 1, right? That's the definition. If she got 0, it collapsed to 0, right? This is still 0, 0, 0 if BB collapsed to 0 BB. Make sense? And that's why we have this case after you say that if C3 equals to 2, which is 0, 1, 2, apply NOT gate to Bob's qubit. If it's equal to 0, 0, don't do anything. And that is exactly what we have here. If you get 0, apply identity gate. If you get 1, apply X qubit to Bob's qubit. Okay, so this one implement the first step of the quantum teleportation for entanglement. I know it can be confusing, but anything that doesn't make sense? Any questions? You might not remember the algorithm. You need to go back to trace again. But for what I'm saying, anything doesn't make sense? Right? The most important is that you look at the value of C3, means that you look at the measurement result. But depends on where you put the results, we need to check the register. If it's equal to 2, then we apply NOT gates. If not, don't do anything. Okay? Okay. So then the next step is very simple. Step 2. Alex do another measurement, but she's going to do it on the plus-minus basis. How can we measure in plus-minus basis? We cannot, because by default we are only measuring in the computational basis 0 and 1. So what we do is convert Alex qubit through Hadamard gate. Do you remember that? If you have a 0, when you go through Hadamard gate, what do you get? Plus, right? And if you have a plus, you go through Hadamard gate, what do you get? 0. And similarly, if you have 1, you go through Hadamard gate, you get minus. And if you go through Hadamard gate from minus, you get 1, right? So here is using this part. So if I want to measure in the plus minus basis, I cannot do it. all I need to do is just apply Hadamard gate. Because after applying Hadamard gate, if I get 0, it means that I would have get plus before the Hadamard gate if I measure in the plus minus basis. Make sense? So here it becomes that if I get 0 here, it means that, so let me write it down, right? So at this point, if I get 0 is equivalent to getting plus without the Hadamard gate. Right? Our goal is that without this Hadamard gate, I want to measure it in the plus minus basis. But I cannot. So I apply Hadamard gate, then now I only need to measure in the 0, 1 basis. If I get 0, it means it was plus before Hadamard gate. Right? If I get 1, it means it was minus. And for Alice's goal is that she wants to measure in the plus minus. So if she get plus, that means she is going to get equivalent to getting 0 at this point. If she get minus, she is going to get 1 at this point. Okay? Now, so based on this, if she get plus, Bob doesn't need to do anything. But if she get minus, Bob has to, right? So here she does the measurement and put this in the register 2. And then we go to this step. This step says that if this register is 4, right? For example, if she get, so let's continue, right? So this part, and then we continue to here. This C3 will be equals to 110 if A collapse to 1, sorry. You see that if I measure 1, right, then Q2 will become 1. Then I keep propagating, this is 110. And 110 is what? 6. So here say that if it is equal to 6, I'm going to apply a Z gate. That is because it is negative. But it's also possible at the previous step here, I might also have 0, 0, 0 in this case. Can becomes here 1, 0, 0 if A collapse to 1, right? Because here I might get 0 or 1. So at this stage, I can have 0, 1, 0 or 0, 0, 0. At this stage, I can get 1, 1, 0 or 1, 0, 0 if this collapse to 1. So that means that if I get 1, there are 2 possibilities, either 4 or either 6. But they won't happen at the same time. That's why we have 2 of them, to take these 2 into account. When it is 4, apply Z. When it is 6, apply Z. Otherwise, for other value, it means this must have measured 0 instead of 1. Then I don't do anything. Okay, and then finally, we measure this 0 qubit to store it, and then look at the output. Pretty confusing, right? Any questions for now? Yeah. Say again. Initial state for everything is 0. Suppose which one is 1? Yeah, Alex, here I just put 0 for simplicity. But this is supposed to be a superposition, right? Alpha 0 plus beta 1. And you will still have the same thing, because this is just the same circuit that we have been using. We already proved that we can do quantum teleportation. gate before tele. You mean at this part? That if you put a NOT gate here, you are just trying to generate the state for Alex. You are assuming that her state was 1, right? That's why you want to generate from 0 to 1. But here, this is a, yes, for this circuit itself, it's kind of meaningless because they are all 0. But however, if we will have the capability to initialize this circuit at alpha 0 plus beta 1, this is already the full quantum teleportation circuit. Make sense? Yeah. So this can be concatenated to another circuit. Maybe you did a lot of computation, you get alpha 0 plus 1, and then you continue to do the teleportation. Okay, yeah.
That's in the step 2, right? The qubit number 2 imager. So it collapsed to either 1 or 0, right?
Yeah.
So can we use the qubit 2 directly to control the step 3 instead of
Directly? No, because this is just the architecture in Qiskit, in Qiskit. So you need to look at the whole number of this register. I understand what you mean. So he's kind of saying that, can we program it such that if C, the second bit of the classical register equal to 1, then I apply Z. Otherwise, don't do anything, right? Yes, if you write your own program. But for this interface, just for this graphical interface, then you cannot do that. Maybe you use Jupyter Notebook, you are allowed to do that. Yeah, that's a good point. This is just purely due to the limitation of the graphical interface. And I used it a while ago. I don't know, it maybe they already have a feature like what you said. I don't know. So just pay attention to what, yes, yeah. Good question. But this question means that you understand what we're talking about. Okay. Then before we finish, I want to talk about another thing called entanglement swapping. So now we know that we have this quantum teleportation from Alex to Bob through this quantum teleportation circuit. Now if I have an entanglement with another qubit, now if I quantum teleport Alex's qubit to Bob's qubit, what will happen to the entanglement? And ideally, you probably will think that then the best should be that Bob will now entangle with Carlos. Right? So at the beginning, Alex entangled with Carlos. Now you quantum teleport Alex state to Bob. Then at the end, Bob should entangle with Carlos. Which philosophically makes sense, right? Because last time I said that if you prepare enough atom, electron, or elementary particle in Mars and entangle with it, I can quantum teleport all my states to Mars, and then the one on the Earth will collapse, become some random atoms because all the wave function got collapsed after measurement. But then I will appear in Mars at no time, right? Because I teleport all the states of all my atoms and molecules and electrons to those molecules in Mars, right? And then if I have a good relationship, let's say I am married, my wife, and let's say love is really due to entanglement, right? If you assume the wave function has this type of relationship is due to entanglement, for example, then is the one on Mars still married to my wife after I quantum teleport to there, right? So in some sense you should, right? So that's why I say philosophically this should make sense. So this is just to show you that if you got entangled with another qubit, once you quantum teleport to another qubit, that qubit will be entangled with the original one. Okay? And how do we see that? You can look at my book to see how to do the qubit by qubit. But the result is that at the beginning, Alex and Carlos, right? This is the most significant qubit, so C is in front of A. CC plus 1 0 0 plus 1 1, right? After quantum teleportation, it becomes 0 C 0 B plus 1 C 1 B, because now Bob is entangled with it. If you try to do a measurement, you will see that Bob is the most significant bit, least significant bit, and Carol is the most significant bit. And they are entangled because you see that whenever Carol is 0, Bob is also 0. Whenever Carol is 1, Bob is 1, right? So they are fully entangled. And these are all the possible measurement outcomes. There are no other possible states. Like, for example, 0, 1 between Carlos and Bob. So I will just quickly go over this in this way. Is that okay? Okay, so try to implement on IBM Okay, so we are done with this part. Now we already done quantum teleportation. It's actually not that easy. But now we will start looking at quantum algorithm. We spent the half of the semester go through those